So after Wendy and Kanani, the confession of experimentalists who do calculation made it easy. So I fully recognize the danger of garbage in and garbage out to calculation. Also the need of support from a modeler. So that I have working with, as a prototype of your educational program, worked with Renata on using her vibration density of states program. I worked with Boris, tried to learn how to do hydrogen in dense magnesium silicates. Also using the UCL program, try to understand how to calculate thermal equation states using AMD calculation. So today I'm going to tell you, rather than how to do calculation, I'm going to tell you what has not been done, what's need to be done from the standpoint of experimentalist. I have to say, you probably agree that in the recent few years, that the ab initio calculation has rivaled the experiments. The experiments provide ground truth or benchmark, but the calculations has put us in a pressure and temperature condition which cannot be reached by experiments. So I'm going to focus on the elasticity at high pressure and high temperature in a much broader sense. So we have a simple goal, which is to model the velocity, model the seismic observations. Here I'm showing you the P velocities as a function of depth for the Earth. I'm showing you mineral model, which is calculated from the mineral properties. I'm showing you the PREM model. This is a radial model, but we have to recognize the tomography is also a very important model for the deep Earth. As you can see that it fits pretty well, but not perfect. So to understand some details, for example, in the discontinuities, you see the velocity jump are different, and you see the slope in the transition zone are different. Why are they different? They can be explained by many reasons. It can be water. It can be we don't understand phase transitions very well. It can be texture, etc. So calculation can help understand those reasons, those problems. So what do we need from calculations? If you want to start from a mineral model, say, let's pick one, perlite or Heisenbergite or pyroxenite. You took a bunch of chemical composition. You want to put it into the phase equilibria, partition into different minerals. Then you do average using the elastic properties, thermoelastic properties from each minerals. Then you calculate the velocities for your bulk rock. And then you derive the P velocities, shear velocities, and possibly the bulk sound velocities to match the seismic observations. So here are the parameters we wanted from both experiments and both the calculations. We want to know equilibrium states. We want to know isothermal, bulk modulus, thermal expansion, and all the temperature dependence. And then we convert it to adiabatic bulk modulus. So thereby we can have a comparable velocities. And if you look into the literature, there are two very sort of useful method for giving those parameters. One is Renata's group has developed the lattice dynamics coupled with density functional theory. The second is the UCL group, which Artem's method of doing molecular AMD, molecular dynamics method. And in the top method, calculate the phonon density of states at 0 Kelvin, then use quasi-harmonic approximation to derive the thermal properties. The method is, I consider it's a very high precision calculation, but the assumption, the quasi-harmonic approximation has been discussed in Renata's papers, so the details in those papers. The AMD calculation also had problems. You know, the LDA or GGA, because they under or overestimate the pressure, so when you derive the equation of states, you have to using the experimental data to correct the pressure so that to match the experimental data. And also it requires a long calculation for material to reach equilibrium at high pressure, high temperature. If you do a 1 femtosecond step, you end up need 2 or 3 picosecond of calculation to reach equilibrium. And longer possibly will improve the accuracy, but its calculation time demanding. So, but we have limited amount of minerals in the mantle. Here are the phase diagrams in the upper mantle. And lower mantle, we have olivine, pyroxene, and high temperature, high pressure formed pyroxene. You have wazilite, and garnet, calcium perovskite, ilmenite, stishovite, and go to lower mantle, perovskite, calcium perovskite, and magnesium oostatite. So then look at the experiments and the calculations. We have quite a lot of information about the major minerals. The experiments are limited. We have to recognize that a lot of measurements are not along the geotherm, and we need calculations to help us to extrapolate to the mantle model. Then from the DFT, you can see there's for the high temperature thermal equation states, there are major minerals. Well, still some needs to be calculated, I think, but that to understand the details of the velocity model, the details come from the cation ordering, the effect of water, the effect of iron. None of those has been calculated at high temperature. Well, even though we have some speakers who talk about the cation ordering or spin states, they are calculated at 0 Kelvin, and the temperature probably extrapolated to the temperature. So also the dense hydrous magnesium silicates, the phase D I worked with Boris, is also at 0 Kelvin. As you can see, this is a blank canvas for people to do calculations on, to calculate the high temperature properties, even though it's elasticity. And to go beyond, what can affect velocities? And there's one thing that I haven't seen any simulations is the inelasticity. The reason inelasticity is important is the measurements using high frequency method, gigahertz interferometry or Brillouin scattering, they are really high frequency, but the seismic frequency is millihertz. So if there is a frequency difference, which we call the dispersion effect, the velocity can be slowed. If the velocity can be relaxed in the mantle. So how much do we know about this effect on the velocities? Well, I'm giving you an example here about phase transitions. Phase transition can be a very important mechanism to slow your velocities, especially in the bulk, because the bulk attenuation, P velocity can be slowed. I'm giving you the models. The unrelaxed is from both the calculation data, from the calculations and the experimental data on the P velocities, a constructed model without, do not consider the relaxation effect. And then the other one is to consider the totally relaxed the case due to phase transitions of the Earth. The red curve is not realistic in the mantle, but I know, that there is some percentage of relaxation due to the phase transition, due to the inelasticity. So maybe to understand this effect, one need to understand the processes which will affect the volume or shear strain. For example, in phase transitions, what is the kinetics phase transitions? That will slow your velocity. Kinetics includes how fast the new phase grow out of one phase, how the high pressure, low pressure phase grow out of the low pressure phases, and also how cation diffuses in the high pressure, low pressure phases to accommodate the phase transitions. All those are time-dependent properties, and I think that is in the urgent need to understand it deeper. So to follow Renata's guideline, and the calculation of elastic constant is using the VASP and PWSCF. The high temperature is through the calculation of phonon density states using from the zero calculation. For the AMD calculation, you just set up the temperature, do a long run. The time, I don't know the exact time, but I estimated the time. I think the phonon density states take a longer time for the relaxation. For the AMD calculation, when I was doing the calcium silicate perovskite, I got a message from the computing center said, I used up 2 million computation unit of time. Well, first of all, the calcium perovskite is sort of a complicated issue. There are many authors give you different results. I was eager to reproduce all of them. And the second is that I don't know what I'm doing, so I did a lot of tests, wasted a lot of time. But I'm able to reproduce the experiment results. I'm pretty confident with that. So what do you like to see in terms of the infrastructure development? I'm I'm not answering the question. I'm expressing my opinions from end user's point of view. For me, all I need is a PC and a login account and the knowledge that I have CPU time I can use. So I need accessible computer resources. I need a problem-focused code development, support team. I need somebody to email to and somebody I can call when I had error in my calculation and to understand what I'm calculating. And tutorial workshop will be helpful. Educational material will be useful. So to make it short, hardware, yeah, PC with the SSH and login account. Tutorial, I find, from my personal experience, I find Espresso package, the examples are quite useful. That to understand, try to use the vulnerable density states calculation. And so I'm done.
Oh, thank you.
Yeah. Yes. Yes, Dave.
Go ahead. Oh, I just wanted to ask two quick questions. One was, so those extra mechanisms you're talking about, so this would actually be as the seismic wave propagates through, you get sort of frequency-dependent phase transformation because you're changing pressure, or potentially it couples to migrations of defects and things like that.
Yeah.
That's the mechanism kind of you're thinking about.
Yes, that's what I propose.
And has that been, I mean, people have studied this in different systems, maybe not in deep Earth systems. Do you have a sense, is that do we assume that those mechanisms really should be active and we've just been kind of ignoring them for now?
I think it should be active.
Okay.
From my experiments. I did a multi-animal experiment.
Okay.
I see, but in a different scale. But I'm trying to create a model, extrapolate to the Earth with a smaller scale.
And then just quickly, so maybe this is also to Artem, I wasn't, that free energy expression from the ND, you can converge that with full ab initio ND in whatever your 20 picoseconds you have?
What is the expression we're talking about?
There's an expression, sorry, there's an expression for the free energy in terms of a kind of integration over phase space, which I guess you basically sample with molecular dynamics from an ab initio MD expression for the free energy.
Integration?
Well, it's not thermodynamic integration, right? It was a direct ND simulation, wasn't it?
Can you show the equation so that I know what we're talking about?
And I was just amazed that you could converge that in the 10 to 20 picoseconds.
The direct free energy calculations from MD would be extremely slow conversion.
Yeah, that's well. Maybe I misunderstood what that was.
Or thermodynamic perturbation theory, this converges fast.
Right. Maybe that was maybe it was a perturbation. Maybe it was a delta U between images. Yeah. Was that what that was? Okay, that wasn't absolute. Okay. That makes more sense. It's a perturbation then.
Okay, did they?
My question
Yeah.
actually.
Oh. I always do that. I don't know why. Yeah, there you go. The second equation.
So that U is a delta U between two phases?
Oh no. This is a basic equation from
which.
which.
Harmonic. This is a harmonic problem.
Yeah. Well, the equation below is general, is anharmonic, and nobody uses it. People only use it to derive equations for thermodynamic perturbation theory. So
okay.
this is
Well,
starting
so
point for the equation.
you didn't do a brute force integration of that expression?
No, nobody does.
Okay.
My question actually is related to that's the first question. So you mentioned that you want to study the kinetic of the phase transition. So that's want to couple with the seismology wave. So
yeah, the kinetics of phase transition defines the characteristic time of a certain process which causes relaxation. Then if you use the inelasticity,
okay.
Then if the measuring method, the frequency of the measuring method is close to your characteristic time of a certain relaxation process, you get very large attenuation, and you get the largest gradient of the velocity change.
What's the time scale of the
seismic frequency?
Of the kinetic process we talk about, the phase transition?
In my measurement, it's about a second to 1,000 seconds. It's very close to the seismic period. So.
Okay.
I have a question.
Oh, quick one. 10 minutes for
Oh, I thought 10 minutes for my question. We managed to calculate the speed of phase transformation from perovskite to post-perovskite. Is it relevant for computing attenuation, or it's a diffusion control process rather than transformation control process?
Okay. In my model, when I want to know the diffusion process, I'm talking about in a binary loop, in an ion-bearing